Okay, we're given a situation where we have balls rolling down 3 ramps, and let me just kind of depict that. Here's a ramp, and it continues on, dot, dot, dot. Okay, another ramp, and another ramp, and we assume these are identical ramps even though I didn't draw them the same width, and they all have the same starting point, and we have a ball ready to start down this ramp. And then we have another ball on this ramp, another ball on this ramp. We release this ball at t equals 0. We release this ball at t equals 3. And we take a pool cue, so I'm going to draw a little pool cue here. And we give this thing some initial velocity at t equals 2. These ramps have different slopes. Least acceleration here on this ramp. Greatest acceleration on this ramp. Now I'm writing this down pretty poorly because this video is going to be embedded in a document that gives these conditions very explicitly. But this is the first one to start, then this one starts, and this starts from rest, this starts from rest. This is the only one that's given an initial velocity. So this one's going to get out ahead of either of the other two. This one is then going to start, but it's going to have a greater acceleration, so you expect it to be eventually catching up with this one. This one is given an initial velocity. The other two, well, this one is going to be ahead of it because it gets its initial velocity at t equals 2. And the acceleration here is greater than the acceleration here, so this one is going to catch up with this one. Now, the question is, does this one catch up with this one? So we ask those sorts of questions. Anyhow, in order to model the position function, well, position functions are going to be quadratic, as you should know at this time. And we'll talk soon about exactly how that follows from the fact that acceleration is assumed to be uniform. Okay, but we assume uniform acceleration so that our position function will have the form x naught plus v0xt plus 1/2 axt squared, where x sub 0 is the position at t equals 0, v0x the velocity at t equals 0, and a sub x the constant acceleration. Okay, so what can we do with our first situation, the first ramp? Well, we know that x naught has to be excuse me, 0, because at t equals 0 the ball is released from rest. And it's released from rest, so v0x equals 0. And also the acceleration was given to be 30 centimeters per second squared. So it follows that our position function is a very simple function. The x naught is 0, the v naught x is 0, so that all we have is the 1/2 axt squared, which turns out to be 15 centimeters per second squared times t squared. Okay, that was easy. Now the second situation is a little more complicated. Okay, we know that x at 3 seconds is 0. We know that the velocity at 3 seconds is 0. So that means what? Well, x of 3 seconds, well, x of t is x naught plus v naught t and so forth. We're going to call this x sub 2 of t. So we have, we call this x 0, 2, v0x2, and ax2, okay? So, x2 at 3 seconds, and I'll put the 2 on here and a 2 on the velocity, just again to indicate that this is the second ball on the second ramp. If we plug 3 seconds in for the time, then our function will have a 3 seconds here, be 3 seconds squared here, acceleration here, and initial position here. We don't know what the initial position is. And I say initial position. The initial position is 0, but the initial instant here is at 3 seconds. We want to know what x is when t equals 0, and that's what we mean by x sub 0. So x sub 0 for the second function is unknown. Okay, maybe the ball was sitting there. Well, let's talk about what that means in a minute. The t equals 0 velocity of the second ball is unknown. We do know the acceleration, and of course the clock time is 3 seconds. So we have this equation with two parameters, x sub 0, 2, v sub 0, 2, both unknown. We only have one equation, but of course this equation is equal to 0 because the position at 3 seconds is 0. How are we going to determine anything from a single equation with two unknowns? Well, we're not. But we can get a second equation very easily because we have information on the velocity. And the velocity, as everybody knows, I hope, is the derivative of the position. So v2 of t is the derivative of x2 of t. And the derivative of this function is very clearly, the derivative of this is just v0x, derivative of this is just at, and of course we use v0x2 for the velocity, initial velocity of the second ball, ax2 for the acceleration of the second ball. We get this function. And we know then that since the velocity at 3 seconds has to be 0, if we put 3 seconds in for t, we're going to have an equation with only v0x2 unknown. So we can solve this equation for v0x2 and we're going to get negative 150 centimeters per second. So v0x2, and we'd go in where v0x does here, negative 150 centimeters per second times t. The acceleration, of course, the 1/2 50 centimeters per second squared times t squared, half of 50 centimeters per second squared is 25 centimeters per second squared. We're going to have this term. And we need to know what x02 is. Well, we've now determined v02, so we can put that in here. That's negative 150 centimeters per second. Multiply that by 3 seconds, we get negative 450 centimeters per second. Centimeters, I'm sorry. And here we're going to get what? That's going to be 9 times 25, 225 centimeters. So we have negative 450, negative 450 and plus 225 centimeters. All these have to add up to 0, which means x02 has to be negative 225 centimeters. So again, all we've done is we've set up an equation for the position x2, for the velocity function, which I'll call v2. And we solve these two equations simultaneously for v0x2 and x02, and we get this function. We also specify t greater than or equal to 3 seconds. Now, that seems a little strange because x02 is where this thing is supposed to be at t equals 0, but this thing doesn't even start till t equals 3 seconds. Well, there's an interpretation of this. It's simply that if this was undergoing uniform acceleration before t equals 3 seconds, and it probably wasn't, but if it had been, this is where it would have been 3 seconds before it was here ready to start. So maybe it was rolling up the ramp, 225 centimeters down the ramp, rolling up the ramp, accelerating at 50 centimeters per second squared, which would be in this direction, which means it's slowing down and it's going to come to rest right here exactly at the t equals 3 instant. We could make that interpretation, which makes the negative 225 centimeter position and the negative 150 centimeter per second velocity sensible. If this thing was 225 centimeters down the incline, moving at negative 150 centimeters per second, which would mean 150 centimeters per second in this direction, accelerating with a positive 50 centimeter per second squared acceleration, you can check out and see that it would be right here at t equals 3, and it would be at rest for an instant. Okay? So there is an interpretation of this, but in reality, the thing is probably just sitting there waiting for somebody to release it. Okay, well, we do the same thing for this ball. Now, the only difference here is that your x of 2 seconds is 0. Your v of 2 seconds is not 0. Remember, you gave this thing a 40 centimeter per second velocity at the t equals 2 instant, t equals 2 second instant. And the acceleration is 40 centimeters per second squared. Well, we can set up our x of 2 seconds, which should equal 0, and our v of 2 seconds, which should not equal 0. It should be 40 centimeters per second. And incidentally, in class, I just carelessly wrote down 0 here, which caused me some confusion. The graph didn't look like it should, and I couldn't resolve that until I figured out what I'd left off here. So do as I say, not as I do. Be careful you put the right numbers there. Okay, and we could put subscripts in this, x3 and v3, and x03, v0x3, and so forth. We get, when we solve for v0x and x03, we get x3 of t is negative 40 centimeters per second times t, plus 20 centimeters per second squared times t squared. Okay, so that's how we make use of the given information to get functions that tell us the position of each of the 3 balls at any given time. And I didn't write it here, but maybe I should say, and t has to be greater than or equal to 2 seconds, because we do restrict the domain. Maybe it was doing something before that, but there's no information in the problem, in the statement of the problem, that tells you what that might be. Okay, so that's the first hurdle. Being able to take the given information, put it into this format, get 2 simultaneous equations, solve them so you have a position function.